Good morning to all of you. Today we are going to study another very important topic, which is a very important topic for engineers, and that is damped harmonic oscillators. Now, before we study the damped harmonic oscillator, we have to revise the simple harmonic oscillator. So, first of all, we will briefly review the simple harmonic motion. Now, the first question is, why we study the simple harmonic motion? Because in everyday life, whether it is our everyday life or in engineering, everywhere we see there are a large number of examples of this kind of motion, For example, in our everyday life, we see pendulum, that is a simple harmonic motion. Then there is a swing, though sometimes the angle is higher, but very close to simple harmonic motion, swings. And then the guitars, the electric guitars or whatever guitars you play. Then if you go to the atomic dimensions, the atoms vibrates, the vibrations of atoms. Then in the electromagnetic region also, the electrons, they vibrate in the circuits. So there are different examples where the vibrations are there, oscillations are there, and simple harmonic motion is quite important. That is why for us to study. Now I remember just to give you a flavor that how important it is. When I first joined my job in BITS Pilani, long time back, that was 1999. At that time, the first year students, we have to teach, I don't know what is the present scenario. So first year students, the course was vibrations and waves. And the book that was followed was AP French, quite a tough book. And the syllabus was fixed like that because the vibrations and waves and simple harmonic motions, these are very important for the engineers. Now, the second thing is, we say periodic motion. Now, there are 2 or 3 similar terms. One is periodic motion, other is oscillatory motion, and third is simple harmonic motion. Now, every simple harmonic motion is a periodic motion, but every periodic motion is not simple harmonic. Like, the planets moving around the sun, it is a periodic motion, but it is not simple harmonic, because there is no fixed point or a mean position about which it is moving. So it is not simple harmonic, but it is a periodic motion. Similarly, when we say oscillatory motions or vibrations, oscillatory motions, now oscillatory motions is a large family. Within that, a special case is simple harmonic motion. Now in oscillatory motion, obviously there is a mean position and about which it moves. But that particular oscillatory motion may be a very complicated type of motion, like something like this. It is a complicated motion. Now it can be achieved by adding 2 or 3 simple harmonic motions. So harmonic means it is pure simple sine wave or cos wave. So either in a straight line or in a angular small angle, that is your angular simple harmonic motion. So these are the cases of simple harmonic motion. So when we combine different simple harmonic, we get more complicated motions which are of oscillatory nature. But we don't call them as simple harmonic. So that is what the simple harmonic motion is. Let me first, before we begin, tell you what are the topics that we will cover today. So a brief review of simple harmonic motion here. After that, we will start with damped harmonic oscillator. Now, in damped harmonic oscillator, there are 3 different cases I would like to discuss. One is heavily damped, critically damped, and lightly damped. Now, these 2 cases we are not going to discuss much. They are not of much of importance to us at present. We will discuss more about this lightly damped. lightly damped. Now in the lightly damped case, we will take up all these things like displacement, amplitude, energy, two-factor. We will study about these cases. So mostly with lightly damped oscillations. The three important quantities that we are going to see or learn, one is omega 0, which we already know, it is undamped case, natural frequency, natural angular frequency. Omega 1 is the angular frequency of the damped oscillator, and gamma is the damping term. Gamma is a damping term. These are the very important terms. Based on that, we will see that how Q factor, energy, amplitude and displacement. So this is what we are going to study for today. Fine. Now let us see simple harmonic motion. It is a simple harmonic motion. Now what are the properties of simple harmonic motion? It is a periodic motion, obviously, about a mean position. So about a mean position, a particle undergoes a motion, to and fro motion. That is what we have studied in schools. The other property, which is the most important property actually, that is there is a force. And what is that force? That force tries to bring the body to its mean position. The force which is acting on the body when the body is moving, the force tries to bring the body to its equilibrium position. So that force is F. And we call that force as a restoring force. That means it is restoring the body to its equilibrium position. That is proportional to negative of the displacement. This x is the displacement. That means it is a vector. So we are writing here the scalar equation, one component only. So minus x. Okay. So F is equal to minus kx. This is a very well-known equation of the simple harmonic motion that we have studied. So whenever simple harmonic motion we talk about, we immediately this equation comes that F is equal to minus kx. But even then, though we have studied this many times, but sometimes we do have certain confusions about this. So that is why I have put some question marks, because what actually is the F, what actually is the X. So let us be a little bit more clear about it. By taking an example, which is a spring mass system. Spring mass system. Now here there is a block. This block is attached by a spring. Okay. This is in the relaxed position. So there is a spring, a block is attached. Here the block is stretched and it is released. So it is undergoing the simple harmonic motion. The third case is the block is compressed and still it is undergoing simple harmonic motion. Now here as we see there is no force because it is relaxed position. This is your x is equal to 0. In the stretched position when you see, now the body is in the stretched position and it is undergoing simple harmonic motion. Now as you see, this is your x, the displacement x. Now the restoring force, as you see the spring force which is acting towards the mean position this way. This is your displacement x. So if I write minus k of x will be in this direction. So this follows this equation. So the force is restoring force towards the equilibrium position. Third case is over here when the particle is on the other side. Anywhere it is moving this side or that side, we don't mind. The particle is on the other side and the spring is compressed. There what we find, this is the displacement x. This is the displacement x. Now F is equal to minus k of x. F is equal to minus k of x, and that is what we see that F is along this direction. So here it is actually the positive direction minus, this is minus x. So minus is positive. So F is in the positive direction and this is towards the mean position. So what we find from here that this equation contains three important information. One is the force is always towards a mean position, the direction. Second is it is proportional to the displacement of the body from its mean position. And third, the force is negative to the displacement. That means in a direction opposite to that of the displacement. Displacement is a vector from the mean position to the particle. Okay. So now this is clear to us. Now let us see there is a little bit more we would like to see. And sometimes there is confusion, and that is why I have put this question marks. This particular force, whenever the body is stretched or compressed, so what we find that a force is acting on the body when a body is undergoing simple harmonic motion. Now that force is known as restoring force. Restoring force. We can write restoring force also, but we can write F of the spring. F of spring is equal to minus kx. Now this is given to us that whenever there is a simple harmonic motion, a force is acting on the body towards the mean position by the spring. Here it is spring, so we say F of the spring, which is a restoring force, is equal to minus k of x. This is given to us. Now, the question is, what is our goal? What is that we want to do over here? We want to find out what is the goal? The goal is we want to find out the displacement, velocity, acceleration of this particle. So, our goal is, we have to be very clear now, what is our goal? Our goal is to write the equations of motion. Our goal is to observe this motion as well as the force and everything, and represent it mathematically. Represent it mathematically. That is what the goal is. To represent it mathematically, a mathematical expression of the motion of the body. So we are observing the motion of the body and we want to represent mathematically. Now why? Because from that equation we would like to see the displacement, velocity, acceleration with respect to as a function of time and position. That is what our goal is. So let me write this goal. So our goal is to equations of motion, to get equations of motion. Equation of motion. Okay. Fine. So how to write the equation of the motion? That is, this particular step is very, very important. The way to write the equation of the motion is that we write the Newton's second law of motion. That is, sigma fx is equal to max, sigma fy is equal to may. We all know this. Now, why I am doing it is, the reason is, many times we have confusion. Not here, but later. And that is why this approach is very, very important. That we must understand this, that was our goal, equations of motion we would like to write. So, sigma fx is equal to max. Or, this is also written like fx is equal to max. Now, as you see, this fx and the one I have written over here, f of spring, here both are same, but this fx means something different. In place of sigma fx, people also write in the books fx. Fx means the net resultant force acting on the body in the direction x. Now, here the net resultant force, that means only one force is acting. But if there are more forces, then we have to add all those forces. So, for the present case, this fx and here f spring that we are writing, it is the same. But sometimes what happens that we confuse and we think that this fx is basically f of the spring. For this particular case, yes. But in general, no. This represents the net force acting on the body. Okay. So sigma fx is equal to max. because I am writing the equation of motion. So sigma fx, what is the net force acting over here? Minus kx and max. So ax we write d2x by dt square. The moment we write this, immediately we get the equation of motion, or we get the differential equation. From the equation of motion, we are getting the differential equation. d2x by dt square is equal to minus k by mx. So, the moment we write this one, that is the differential equation we got, differential equation tells us how a body or how a particle is behaving as a function of time. From there, I can find out the displacement x, I can find out the velocity, I can find out the acceleration, everything I can find out. So, let us see. Now, d2x by dt square minus k by m into x. Here what we have to see, that I have to find out now the solution of this differential equation. What will be the solution? How to find out? We see that my equation is such that whatever function I choose or whatever be my solution, if I double differentiate it, then I get back that same function with a negative sign. And you know that these cases are basically sine and cosine functions. Sine and cosine functions. So that is what I was telling you in the beginning, that simple harmonic motion. One important point I forgot, the simple harmonic motion can be expressed by simple sine and cosine functions. Not a combination, a complicated combination of them. A simple sine and cosine functions, a straight line motion basically. And that is why we call them harmonics or simple harmonic motion. That means they are harmonic functions. So, sine and cosine, okay, so any of them we can choose. So, let's take x is equal to a cos omega 0 t plus phi as the solution. Phi we have chosen as some initial phase, otherwise a cos omega 0 t. Now here let me tell you, omega 0, why I am writing omega 0? Why not omega? Because later on some other omega will also come. So right from the beginning we are careful now, because we have to study the damped harmonic oscillator. That is why there another omega will come. So omega 0 is for the undamped case. Omega 0 is for the undamped case. That is why we are writing a cos omega 0 t plus phi. Now what you do, you substitute over here and you do d2x by dt square and you write x over here, the things will get cancelled. From there you will see that omega 0 square is equal to k by m. That is what omega 0 square is. So omega 0 is root over k by m. Now here, since I am doing it for a particular body, I have chosen small m. This is a general I was telling, so I took capital M over there. This is for the particular one. We are taking small m, or you can take, one can take capital M also, doesn't matter. Okay, so this is your omega 0. Now, what actually is omega 0? It is a natural angular frequency. Natural angular frequency. Now, again, some term is coming, angular frequency. Why this angular frequency? So that also we have to be clear, and this is natural. That means undamped case is the omega 0. Now, what we find that this particular omega or omega 0 as we have written over here, this particular equation, when we see this particular equation, that means x is equal to a cos omega 0 t plus phi or a cos omega 0 t. If a particle is rotating in a circle with a angular velocity omega 0 and having a radius a, then the projection of that particle, what will be the projection? That will be x is equal to a cos omega 0 t. So if a particle is rotating in a circle with angular velocity omega 0 and radius a, the projection of the particle along the x-axis is a simple harmonic motion. And surprisingly what we find that if you calculate the velocity and acceleration also, their component, that means in the along x direction, then they are also coming from the same picture. And that is what the beauty of this treatment. And here, as we see, this is a particle. There is a particle over here, and at point P, it is shown. This particle is rotating uniform circular motion with a angular velocity omega 0. Now this angle, as you see, it is omega 0 t plus phi, because with respect to time, that is what it covers. And this is your projection of this particle in the x-axis, x of t. So x of t will be a cos omega 0 t plus phi. Displacement. Then, suppose say, we now take the velocity one. So this is the velocity, this is your angle, this is the same angle, this is pi by 2 minus this angle. If you take the component of this velocity along the x direction, this is your x and this is your y, this is your x-axis and this is your x-axis, this is your x-axis and this is your y-axis, everywhere. So if you take the component of this, it will be, the velocity will be r omega, r is a omega 0, minus a omega 0, sine of omega 0 t plus phi, and minus because it is the negative direction. So from this figure itself, we are getting the velocity as well. Then this can be written in terms of x also. So in place of x, if you want to write, you can write it in place of x. Now acceleration, a particle which is moving in a circle, it has an acceleration, centripetal acceleration. So centripetal acceleration is omega 0 square a, omega 0 square a, and obviously towards the center. So if you take the component of that, again the same angle, it will be minus, because in the negative direction this is also x, this is your positive x, and this is your positive y. So it will be minus omega 0 square a cos omega 0 t plus phi, that is equal to minus omega 0 square x, if you want to write it in terms of x. Now these expressions, that means your displacement, velocity and acceleration, you can also get it by differentiating, you can also get. So both way, that is pictorially, you are getting the same answers as you get it by differentiation. So this is all about the our review of simple harmonic motion. The most important fact over here is, we have to remember that omega 0, this will be coming again and again. Omega 0 is a natural angular frequency, that means when there is no damping, natural angular frequency, and that is equal to root over k by m. This is what you know from the first part of this simple harmonic motion. We have to remember it every time. Now we will do the damped harmonic oscillator. But before that, I request you to have a glass of water, and then we will start the damped harmonic oscillator. So after the basic revision of simple harmonic motion, that is undamped harmonic oscillator, we are now in a position to study damped harmonic oscillator. Now here as the name suggests, that damped harmonic oscillator, that there is a friction, there is a viscous force, there is a resistive force which opposes its motion. So that retarding force is F, that retarding force F is equal to minus proportional to the velocity, and obviously it is negative to the velocity, that is why minus sign. So F is equal to minus BV. I am using the same notation as used by Klipner, because we are following that book. So this is the resistive force. It opposes the velocity. It is in a direction opposite to the velocity. So now we will see that when we will write the equation of motion, now there are two forces. There are two forces. What are they? So if I draw a rough diagram of that, our earlier diagram, so here suppose say this is the normal spring, and then this is the extension of that, suppose say extension over here, and suppose the block is moving in this direction V, then the two forces which are working, first is our restoring force, which is F of spring, restoring force, and now we have another resistive force which is opposing its motion, and that is actually your small f. So this is resistive force is what is that? Yeah, F of spring. Fine. F of spring, and this is the resistive force. So now, if I look at the block, our block, then there are two forces which are working. So again, we write equation of motion, sigma fx is equal to max. So on the left hand side, we sum all the forces. We sum all the forces, which is because of the all the real forces. So F of the spring, let me write small over here, that will be better. Yes, Fs. S of the spring plus F because of the resistive force. So both these forces I have written. So algebraic sum of all the forces is equal to max is m d2x by dt square. That is how we write the equation of motion. From there the equation of motion will come. That is the differential equation will come. So f of spring is minus kx, f is minus bv is equal to mx double dot. Rearranging x double dot plus b by mx dot plus k by mx is equal to 0. So this particular equation is the differential equation for the damped harmonic oscillator. Now, here, in order to simplify further, what we do, b by m we write as gamma, and k by m we already know that is omega 0 square. Now, this b by m is coming from b, so we call that as a damping term. Because of this term, the oscillator gets damped. Because of this term, which is an oscillatory term, it oscillates. Okay. So these two terms are there, and which determines the motion of the body. So b by m is gamma and k by m is omega 0 square. These two quantities are very important, which you need to remember, because every time we will be talking about gamma and omega 0 square. So after these gamma and omega 0 square, we write the equation into that form, x double dot plus gamma x dot plus omega 0 square x is equal to 0. Now this is the differential equation, second order differential equation, which we have to solve. So one way to solve is, we substitute x is equal to e to the power of lambda p. So you substitute over here in x double dot, x dot and x, all these places, and then you cancel. Finally you get this equation, lambda square plus gamma lambda plus omega 0 square is equal to 0. The characteristics equation, or the equation that we get. Now, as we see that this equation is a quadratic equation. Quadratic equation in terms of lambda square plus gamma lambda plus omega 0 square is equal to 0. So what to do? We have to find out the solution of the quadratic equation, that is lambda 1 and 2 are the roots of the solution. So lambda 1 2 is equal to minus gamma by 2 plus minus gamma square by 4 minus omega 0 square. Now, these are the two roots of this particular equation. So, what will be my solution? I have two solutions. One is x1, that is e to the power of lambda 1 t, x2 e to the power of lambda 2 t. So these are the two solutions I get for this particular equation. Now the general solution, we write x is equal to a linear combination of both of them. That is x is equal to a e to the power of lambda 1 t, that is one solution, plus b e to the power of lambda 2 t. So that is the general solution of this second order differential equation of a damped harmonic oscillator. I hope I am clear till here. Fine. Now what we will do, that we will see the case that this particular quantity, that is gamma square by 4 minus omega 0 square, is within a bracket. Now there are different cases depending on whether gamma is larger or omega 0, or gamma square 4 is larger or omega 0 square is larger. Depending on that, this will change sign and the different cases will take place. So I write the same expression over here, gamma square by 4 minus omega 0 square. Now let us see what are the different cases depending on this gamma and omega 0. So if this quantity, that means gamma square by 4 minus omega 0 square, the first case is it is greater than 0. If it is greater than 0, then gamma square by 4 is greater than omega 0 square. So this particular quantity is positive. If this is positive, then what you will get two real solutions, lambda 1, two real roots, lambda 1 and lambda 2. One is gamma by 2 plus this quantity, which is a positive root of something positive. Second is lambda 2 is minus gamma by 2 minus this quantity. So two roots you will get. So again, basically the general solution will exactly the same. That is why I have not written, because we are not interested to study deeply about this particular. So I have not written it. So this kind of situation, basically, it will give rise to, if you plot it, it will give rise to heavily damped oscillation. That means you will not see oscillation over here. It will quickly die out. It is heavily damped because of the gamma being larger. That is why damping dominates the oscillation. So it will something look like this, that it is decaying like this. So if you find out the two solutions, that is x1 and x2, one of them obviously is the plus solution. That means if you have these two roots, one will be larger obviously because of the plus sign, other one will be totally negative. So one will be exponentially decaying, the other one will be, something growing like that. But if you find out if you add both of them, that is the linear combination of the both, that will give rise to a heavily damped oscillation. Okay. So xt will be exactly almost the same type, you can write it. The second case is when they are equal. That means gamma square by 4 is equal to omega 0 square. At that time, this particular quantity will be 0. If this quantity is 0, then as you will see, it will have two roots, but both the roots are minus gamma by 2. Okay. So both the roots are the same roots. So lambda 1 is equal to lambda 2 is equal to lambda. That means they are same, and that will be equal to minus gamma by 2 because this quantity is 0. At that time, the solution that we write is a1 e to the power of a1 or a e to the power of lambda 1 t, lambda 1 is lambda t, plus b into t, that multiplied by t, e to the power of lambda t. That is how the solution is for that type of cases. That means when both lambda 1 and lambda 2 is equal to lambda. Again, we are not much interested. This particular case we call critically damped. Here as you see, the plus root is not at all there. Both the roots are minus gamma by 2. So it is exponentially decreasing. If you see this decrease, this is much sharper. This is exponentially decreasing because both the roots are basically negative here. So this kind of motion is called critically damped. Here we don't see any harmonic or oscillatory motion, but it is quickly decaying. So again, we are not much interested in studying about these two cases. That means where damping is very high. Now we come to the third case. Third case is interesting. That is when gamma square by 4 minus omega 0 square is less than 0. Less than omega 0 square. At that time, this quantity is less than 0. Okay. So here oscillation omega 0 dominates the damping term gamma. These kinds of motion we call lightly damped oscillations or under damped oscillations. So we are interested to study these kinds of oscillations. Now in the next slide we will see the mathematics and we will see the displacement term and other terms like your amplitude and how the amplitude decays in detail. But the graph or the plot of x versus t will be something like this. As you can see that it is oscillating, okay, but its amplitude is decreasing at every oscillations with time. So this is the oscillation or this is the damping which we are interested in, where there is oscillation but at the same time it is damping. It is as you see the amplitude is decaying exponentially, but it is oscillating. So in the next slide we will see the detailed solution of this along with the mathematics. So in the lightly damped case, omega 0 square is greater than gamma square by 4. So instead of writing gamma square by 4 minus omega 0 square under the square root, we write omega 0 square minus gamma square by 4 and take the root over minus I outside, that is minus 1, that is I outside, so that this quantity is positive. Now there is an important step. This quantity, this omega 0 square minus gamma square by 4 root over, this whole quantity we would like to write as omega 1. Later on we will see that the solution that we will get, this omega 1 will be our next angular frequency for the lightly damped case. So this is omega 1. Suppose say this is omega 1. So lambda 1 by lambda 1 and lambda 2 is minus gamma by 2 plus minus I, this quantity, that is minus gamma by 2 plus minus I omega 1. Okay. So again, the general solution x to t will be a linear combination of both the roots. So c1 e to the power of minus gamma by 2 plus I omega 1 t e to the power of this particular case into t. There we have done. So this is your lambda 1 t. So lambda 1 t plus c2 e to the power of lambda 2 t, that is minus gamma by 2 minus I omega 1 t. So this is the linear combination of both the solutions, is the our general solution. So e to the power of minus gamma by 2 I take common. It is c1 e to the power of I omega 1 t plus c2 e to the power of minus I omega 1 t. Now whenever you see e to the power of I, you must remember that this gives rise to either sine or cos. E to the power of I theta is sine theta plus I cos theta, all those equations you have read. Okay, so this can be written, this particular quantity can be written as cos omega 1 t plus phi we have included for the phase, initial phase, and a, that is constant, is taken outside, a e to the power of minus gamma by 2. So x of t is equal to a e to the power of minus gamma by 2t, and this quantity can be expressed as cos omega 1 t plus phi. Now this particular equation is now the solution of the differential equation for the lightly damped case. So this is the final solution that we get as a xt. Okay, so what we need to remember, that we have got another member, another player now, which is omega 1, and omega 1 is omega 0 square minus gamma square by 4 root over. Okay, and this is the angular frequency for the lightly damped case, or damped oscillation, because we are studying only this one. Okay, now this particular quantity, okay, one can write like this also, it's okay, x of t. This particular amplitude is very important. Here one has to see that this is the amplitude a into the power of minus gamma by 2t. So this is the amplitude at a time t is equal to a into the power of minus gamma by 2t. Then a is the initial amplitude. So what we find, that the amplitude is decaying exponentially, minus gamma by 2t. So this is very important, and many places the questions, when you will get the questions, this particular formula is very important, this particular understanding is very important. So amplitude is decaying exponentially as according to this expression, that is a e to the power of minus gamma by 2t. A is the initial amplitude. Now, suppose say I would like to compare omega 1 and omega 0. That is, omega 1 is the angular frequency for the lightly damped case, and omega 0 is for the undamped case. What we find, that omega 1 square is equal to omega 0 square minus gamma square by 4. So what does it mean? It means that omega 1 is less than omega 0, and that is what I have written over here. Damped system oscillates more slowly. Damped system oscillates more slowly because omega 1 is less than omega 0. Now, here something more, when you try to solve the problems, what you have to remember, that whatever treatment or whatever formulas that you remember for omega 0, which is 2 pi nu or 2 pi by t, capital T, all those are applicable, all those formulas are applicable for omega 1 as well. Okay, so let us say about the amplitude. So amplitude AT is a into the power of minus gamma by 2t. This is a very important expression or formula. Gamma, we know it is b by m, so we can write a into the power of minus b by 2mt. Now let us define a tau. Let us define a time period tau, okay, time constant, and during that time, that amplitude becomes 1 over e times the initial amplitude. So we write a is equal to e to the power of minus t by tau. So tau will be equal to 2m by b, when it will become 1 over e. So the tau is a damping time constant. It is also known as mean life constant. When t is equal to tau, a is equal to 1 over e a. That means the damping time constant tau is that time when the amplitude will become 1 over e times the initial amplitude. So this is about the amplitude, and this is a very, very important for your problem solving. Okay. Now, let us come to the energy part, because till now we are interested about the displacement x and also the amplitude a. Now, we will see what is the how the energy is changing. Now, obviously, since it is dissipating, since it is a damped oscillator, so energy will not remain constant. So energy will keep on dissipating, that means it will decrease. So energy at time t is equal to kinetic energy plus potential energy. It is half mv square plus half kx square. One can find out V and one can find out that U also. From there one can find out the total energy. Also we can take half kx square. What we can do that we can take one particular amplitude, we can take one particular oscillation, and in that the maximum displacement is the amplitude. So whatever is the energy over there, potential energy, that we can write. So it will be half Ka square e to the power of minus lambda t. Just that is your A is your minus gamma by 2t, just square it. So it is A square e to the power of minus gamma t. So that becomes E0, this is E0, e to the power of minus gamma t. So this is how the energy is changing. That means energy is also exponentially decaying as e to the power of minus gamma t. This is also a very important expression, that how energy is changing. So E0 is equal to half Ks square is energy at time t is equal to 0. And tau is the, suppose say now, we will calculate here another tau, which is the damping time. That is time required for the energy to drop to 1 by E of its initial value. What is that tau? What is the time? So E tau is equal to E0 e to the power of minus gamma tau. Now this becomes minus 1. So equating gamma tau as 1, tau becomes 1 over gamma. That is m by b. So this is the time required for the energy to drop to 1 by E of its initial value. So this is the, you can say, damping time constant. Okay. Now we will come to another important quantity, which is a dimensionless quantity for a damped oscillator. Now that is a quality factor. That is known as quality factor. Now what does a quality factor means? It tells us, it determines the degree of damping. How much is the damping? So the way it is defined, Q is equal to energy stored in the oscillator at a particular time, energy stored in the oscillator divided by energy dissipated per radian, not time, energy dissipated per radian. So this particular ratio will tell us that how effective a particular system is. So energy dissipated. Let us calculate the energy dissipated part. So energy dissipated, we just differentiate the energy expression. We get gamma E0 e to the power of minus gamma t, that is minus gamma E. Okay. That is the energy dissipated, dE by dt. Now I have to find out that how much this is per unit time. Now in time t, how much it will dissipate. That is delta E. Delta E is equal to dE by dt, that is energy dissipated per unit time, multiplied by delta t. So dE by dt we have already calculated, that is gamma E multiplied by delta t. So this is the energy dissipated in time t, but I have to calculate for per radian. So let us see, 2 pi radian is equal to 1 time period t, takes time t. So 1 radian, so 2 pi radian, 1 radian is equal to t by 2 pi. Okay. So t by 2 pi, that is 1 radian. So which is equal to t by 2 pi is 2 pi by t, 1 over 2 pi by t. So that is 1 over omega 1, 1 over omega 1, and that is equal to the delta t. That is what the delta t is, that 1 radian is equal to 1 over omega 1, that is the delta t, and dimension also the same. Okay. So now what we do, delta E is equal to gamma E, delta t we have already calculated 1 by omega 1. So delta E is equal to gamma E by omega 1. That is using these two equations. Okay. 2 and 3 equations actually. 2 and 3. So that is gamma E by omega 1. That is your delta E. So Q is equal to energy stored in the oscillator, that is your E, and energy dissipated per radian. So per radian, that is what we have calculated, delta E is equal to gamma E by omega 1, So that gives rise to omega 1 by gamma, and if we assume that omega 1 is close to omega 0, very light damping, we can also write omega 0 by gamma. So if it is lightly damped, the Q is much greater than 1. It is heavily damped, Q is low. For undamped oscillator, it is infinite Q. So this is about the quality factor, that how effective a particular system is. To find out the quality factor, that is energy stored in the oscillator divided by energy dissipated per radian. Alright. Now there is no space. Let us discuss about the assignment. There are few examples which we can do. So the first is a musician tuning for rings at A above the middle C 440 Hz. A sound level meter indicates that sound intensity decreases by a factor of 5 in 4 seconds. What is Q of the tuning fork? Now, in all these problems, whenever you get the problem, how to attack the problem? The problem is, first of all, you have to see that which quantity it is talking about. Okay, so it is talking about energy. So just go to energy, this energy. Okay, go to the energy expression, and from there you find out the value of gamma. The moment you find out the gamma, you can find out the value of Q, which is your omega by lambda, omega by gamma. So this is how the things are. We will do some more problems, and sometimes it will be about amplitude. So immediately you have to take the amplitude expression, that is this expression. Sometimes mostly it is on amplitude or energy, or it is on time constant. So all these formulas you have to remember, and sometimes omega, how to find out the omega, and from there how to find out the number of oscillations. So omega is equal to 2 pi nu or 2 pi n or 2 pi by t. So these are the few formulas you have to use, and using that you have to calculate in most of the cases gamma, and from there omega, and from there the amplitude, and you have to calculate the whatever is being asked to you. So this is all about the lightly damped or damped oscillator. The next topic that we will cover after some assignment problems in this particular topic is the forced oscillator. All right, the forced oscillator. Again, we will write down the equation of motion. So this much for today, and so what you have to remember is mostly what is omega 0. Then you have to remember the equation, the differential equation for the damped harmonic oscillator. Then you have to remember the solution for that. So that solution, basically there are three different cases, and the third case that we are dealing with is lightly damped one. There you have to remember the expression for the displacement, the amplitude, and the energy, and the time constant, damping constant, and both. Then you have to, the quality factor. So these are the expressions that you have to remember. So okay, thank you for today. And next video we will make on the forced oscillator. Okay, I include here 3 questions so that you can practice a bit and get a feeling of the damped harmonic oscillator. So let me read out the questions. They are very simple and you can practice yourself. In one experiment, a paperweight suspended from a hefty rubber band had a period of 1.2 seconds, and the amplitude of oscillation decreased by a factor of 2 after 3 periods. What is the estimated Q of the system? Now, in this particular problem, what you have to see that what is given to you and what is being asked. So given to us, what is given to us is your time period. Time period is, obviously this is the time period of the damped oscillator. So this is 1.2 seconds which is given to you. And what is being asked is Q. Q is being asked. And that is Q is omega 1 by gamma, which is being asked. That you have to find out. Okay. Other thing that is given to you is regarding the amplitude of oscillation, how the amplitude is decreasing. So you must just write the amplitude equation, which is your AT is equal to A e to the power of minus gamma by 2 into T. Alright. Now, the amplitude of oscillation decreased by a factor of 2 after 3 periods. So 3 periods you can find out the time. 1 period is 1.2 seconds. 3 period is multiplied by 3. Very simple. And you have to take the ratio of them. That means at time t is equal to 0 divided by after 3 periods. So at time t is equal to 0, amplitude will be a maximum. After 3 periods it will decrease, and that ratio is equal to 2. From there you can calculate the value of gamma. The moment you get the value of gamma, easily you can calculate Q, because omega 1 is what? Omega 1 is 2 pi by T, and T is given to you. So you can calculate the value of the quality factor Q. Alright? Fine. So here this particular expression is very, very important. The next question. An underdamped harmonic oscillator has K given, mass given, and B given. How many oscillations does the system make before the amplitude decreases to 1 over E of its initial value? So again, what is given to you? K is given to you. Then mass is given to you. And B is also given to you. Okay. What are the things that we can calculate from here? K, M and B. Obviously we can calculate omega 0. This we can calculate because omega 0 square is equal to K by M. And also you can calculate gamma, which is B by M. This also you can calculate. So both omega and gamma you can calculate from here. Now the question is, how many oscillations does the system make before the amplitude decreases to 1 over E of its initial value? Again the same problem, same question of amplitude. So we can write down the amplitude once again. AT is equal to A e to the power of minus gamma by 2 into t. Now this amplitude has to be 1 over e times 1 over e. That means this gamma by 2 t has to be 1. From there you can find out the value of t. The moment you find out the value of t, if you know the value of capital T, that is the time period, you can find out the number of oscillations. So now your next goal is to find out the capital T. To find out the capital T. Now how will you find out that? How will you find out capital T? Here we will see another important formula which we have studied. We have to find out the capital T. That means we have to find out the value of omega 1. So we have to calculate omega 1. How can you calculate omega 1? We can calculate omega 1 from omega 0 and gamma. How? Using the relations that we have studied, that is omega 1 is equal to omega 0 square minus gamma square by 4. From this we can, omega 0 we know, gamma we know, from there we can calculate omega 1. The moment you calculate omega 1, you get the value of t. The moment you get the t, small t, that is the total time, divided by the time period, it will give you the number of oscillations. So the questions are simple, just you have to apply the formulas. Now the third question, a mass attached to a spring is set in vibration by displacing it from equilibrium at t is equal to 0. After 10 seconds, the amplitude decreased by 75% and the damped period is 2 seconds. Write the differential equations of motion from these two observations. Very simple question. So as we have seen, the differential equation for the damped harmonic oscillator is x double dot plus gamma x dot plus omega 0 square x is equal to 0. So what we need actually, we need two terms, that is your gamma, and we need to omega 0. These are the two terms we need to calculate. Okay, so after 10 seconds, now again the amplitude is given to you. After 10 seconds, the amplitude decreased by 75%. So if you write the expression for AT is equal to A e to the power of minus gamma by 2 into t. So 10 second, after 10 second time is given to you, the amplitude decreased by 75%. So it will be, you can write 3a by 4, 75% is equal to A is e to the power of minus gamma by 2 t. From there you can get the value of gamma. Damped period is given to you. So T, capital T is also given to you. Now gamma you have got, capital T you have got. So only thing you have to calculate the omega 0. Again the same technique of the question number 1. Omega 0, we have to calculate omega 0. So how will you calculate omega 0? Exactly the same equations. That is omega 1 is equal to omega 0 square minus gamma square by 4. So from there we can calculate the value of omega 0. Because time period t is given, from t we can calculate omega 1. And once you know omega 1, we can calculate omega 0. And the moment you know omega 0, you can write down these equations. So this is just a little bit of applying the formulas, and the time period t and how you are calculating omega 1 from the damped time period. These are the kind of things you have to see. So I hope all these three questions are clear to you, and you can try yourself, verify the answers. Thank you.